Hi, hello. Hi, thank you for attending this new and interesting webinar.
Well, today Ronald Siat and me, Roman Martin, we are going to present the fiber reinforced concrete capabilities from CivilFEM 2021, CivilFEM powered by Marc. As there are many new people here, we are going to do a small introduction. Today, many new people are following us. So we are going to do a small introduction of CivilFEM powered by Marc. CivilFEM powered by Marc is a high-end general purpose finite element software that is focused in civil, structural, and geotechnical engineering. And well, CivilFEM uses Marc from MSC Software, which is one of the most powerful nonlinear solver. So CivilFEM powered by Marc is oriented to all advanced analysis in construction and civil structural sectors.
And Master Builder Solutions is a specialized company in advanced chemical solutions for construction. And in this case, they develop the master fibers that are advanced fibers for concrete reinforcement. If you would like more information, you have there here in this slide the website and the email for the contact.
Well, today we are going to see three models about fiber reinforced concrete, focusing nonlinear analysis and design. We are going to start with precast tunnel lining, a segment, and also analyzing the whole tunnel. Then we are going to analyze fiber reinforced pavement under shrinkage effect, plus traffic loads on it, and see cracking, how cracking is happening, and difference of using fiber reinforced concrete and not. And finally, we'll see an example of precast modules for architectural issues. Well, in previous webinars for new people, we saw capabilities of CivilFEM for just generating models, doing code combinations, and checking the models in post-processing, ULS and SLAs, concrete checking, calculating reinforcement amount, cracking, so on. So we did a webinar. You can follow it in our YouTube channel. Also, we did a webinar about pre-stressed concrete. It can be applied to any type of models for cells, beams, or solid elements. And also, we did nonlinear concrete webinar where we compare beam test loading until the collapse of this beam with CivilFEM results with the load deflection curves, where we obtain for bending failure different reinforcement configuration for bending failure, this case, or for shear failure, this other one, this curve, and the same curve similar in CivilFEM, and shear failure in this case, these cracks. And finally, we did a final concrete webinar about thermal structural couple analysis. We saw a concrete beam under fire and the collapse of the concrete beam due to the fire and the reduction of the material properties due to the temperature. And also there are examples about ambient temperature and radiation and the effect on the structures, and another model of early age concrete and the heat due to the maturing of concrete. So well, now just to complete these webinars, we are going to see this webinar about fiber reinforced concrete. So we are going to start with a precast tunnel lining segment. And well, just for introducing the steps for fiber reinforced concrete, the different codes and standards requires a beam test. This beam test is fiber reinforced concrete with a crack, induced crack here on the bottom, and some loads. There are different type of beam test with one unique load in the center, two loads, both sides, different sizes, depends on the codes. And then from this model, you obtain deflection versus forces. So you obtain some curves like this. Codes and standards just give some requirement about minimum values for certain points of these curves that is obtaining to ensure ductility of these models. So well, the first step we can do is having a similar beam and follow those steps to try to obtain the same curve force deflection of the model. The target of this beam is obtaining the material property of this model. There's a material, the material properties is based on stress-strain relationship like this, and well, there are codes and standards gives some model correlations between results that are obtaining from this model test, just to convert them into stress-strain curves. But you can obtain some points that can be improved, adding new points and performing this test to adapt the software results to the test results. So well, we've started with that model. So well, first in this model we started without any type of deflection. For applying those loads, we just created a node here that was rigid connected to these 2 points where those loads are applied, and applied here a displacement. So well, the displacement, we could obtain different deflection values, cracking, and well, an example, this other value where cracking is starting, this point until the collapse of the model. I'm plotting those results, so we obtain this type of curve. Here you can see, as I applied in this node a vertical displacement, what I'm plotting is reaction force versus displacement of one of these nodes. So reaction force is negative, so I obtain this type of curve. But if I convert in force versus displacement, I have here my slide, we can see that these are the tests that were performed in this case, and this ASTM beam test, and these are the CivilFEM values. I've been modifying these points for being a little bit conservative. You can see here different tests, 4 tests of this segment model. Just crack stress was between 30 and 40 kilonewtons. Just I modify this, I added those values to be conservative with that value, and then the maximum load on this model is about depends on the model, over 40, over about 35. So just I keep this 35 and collapse at 4 millimeters. Well, I'm following this example that were provided by the old bus that now it is Master Builders, and this example was a real project that were done by Master Builders that provide us these models. And well, here in this we are following this paper where they analyze the loads that are applied, results that they are obtaining, and we follow this model with CivilFEM. So well, now after obtaining these values, as I said, I've been conservative to have sort of envelope, just a conservative envelope of this test, and having the final collapse at about 4 millimeters. I've used these material properties in the lining model. This is lining model, lining segment model. So in this, I've done the same procedure. I've applied boundary conditions and a load on top that is displacement, and I get the loaded versus displacement force. To generate these models, is very simple. CivilFEM has different tabs to create the models, starting with the environment to select the active codes we would like to have, the geometry, where we generate this model. It's simple, just extracting these arcs, generating these primitives and these volumes, and extracting them and generating the model, then they creating the material properties and mesh and solving it. So well, for creating this behavior, this material behavior, just clicking here, we have a long list of materials based on different codes and standards. This project was in USA, so they use an ACI material. It was 1,000 is, and just the way to put these properties is selecting the material, clicking here, and then you have the linear elastic material behavior. First step is to convert to nonlinear behavior for compression. So I'm adding certain loads and isotropic plasticity model. So now the analysis diagram that I'm using for solving are these. They are time-dependent material properties. Fiber reinforced concrete behavior, they don't have, I'm going to select the 28 days only, just for you to see it. All those graphs are time-dependent material properties, so you have many curves. So this is the basic behavior of concrete, a parabolic law. But for fiber reinforced concrete, this law is more bilinear. We'll have something like this behavior. So from the compression test, I mean, you should modify these values for the 28 days. You can also copy and paste from an Excel file and modify these values to adapt the regular concrete behavior to your test from the fiber reinforced concrete. So after modifying this to adapt to the fiber reinforced concrete behavior, we just go to the cracking and post-cracking behavior. First, we click here to consider cracking, and first we can set cracking stress. The cracking stress could be constant or temperature or age dependent. Temperature is when we are analyzing a fire, an example where material properties depends on temperature, high temperatures. We could reduce crack stress, and also of course in age for early age concrete models. In this case, we are not using them, and we keep constant the crack stress because we are solving for 28 days. We are not considering evolution of these properties. But we have to set the behavior for post-cracking. So that is clicking here, variable softening modulus for post-cracking, and clicking here, then we set these properties. So I'm going to set it in megapascals. So here we are adding only the post-cracking behavior. So we start with the cracking stress. In my case is 3.5 megapascals. And then we apply strain versus, we set different strains values. In example, I'm adding here 0.001 and insert it, and it is going to be a crack strain of 1.5. Then we add another value of 0.005, and we increase it again to 4, and so on. So we are generating, sorry, I'm going to delete this. So we are generating our curve for post-tension behavior based on the test results and the fiber content behavior. So we are setting here these values, these parameters, and adding other So well, in this way, you create the different input for post-cracking behavior. And well, I'm going to cancel it. And well, in this way, you input your values. Other important parameter is the shear retention factor. This is the shear that is transmitted through the crack, and it should depend on the crack width. So in the same way, you set different values here, depending on the crack width. And this should be starting with 1. It means before crack happens, a full shear transmission. And when the crack width is wide enough, there's not a shear transmission through it, so it is 0. This curve used to be parabolic low, and there's a lot of documentation about these values. And finally, the last value you can set with CivilFEM is the crushing strain. With this strain, you set here crushing strain, example 0.35%. It means that when this plastic strain is reached, the element is broken and has no stiffness. Then it has 0 stiffness from that moment. That behavior is completely different from the crack strain, that the crack strain can be closed and then it has full compression transmission in that point. Well, just after creating your material models and material properties, to create the mesh, apply the loads, and then you can plot, after solving, you can plot the results, cracking results. Well, after the configuration of the material properties and the different models to be sure of the input of the concrete, fiber reinforced concrete, starting with the beam model, then generating the correlation between the force versus deflection of the beam model to the stress-strain relationship of the material, and also launching. Also, you can launch several times this model to generate more points in this curve and to adapt more to the test you're having. Next step, you can test the lining segment, and after having the full behavior of the lining segment, comparing the real test with the CivilFEM test, the load versus deflection of this segment. Other models that can be performed with CivilFEM is a full ring analysis. For the TBM machines, there's a cell that is used for the construction. There's a small gap between the cell and the rings, and then between the rings there are different joints, transversal and circumferential and longitudinal joints that can be analyzed. So in this case, we also created a model. We have that model here. So the first plotting this is the model that we've created to analyze in detail this rings behavior and this joint. First, we create the section and we solve the construction process. First, only soil, then the excavation with a small gap for the tiny tunnel lining, and then the last step, we add an overload on it, on top of it. So well, after creating this model, we can check the pressure on the. We can check displacement. Well, the scale is very big. I'm going to reduce it. So we can check first total displacement on the model. We could check the ring behavior, the rotation in these gaps, and also we could plot, we could analyze bolts and some other results. You can see here, there are some bolts connecting these rings. We can also obtain from this model forces and moments of this model, just to analyze kilonewtons, the load we are having, and just designing these bolts and connection and checking it. So the next level of models that can be performed with CivilFEM is analyzing these joints and these bolts and the rings behavior with these other detailed models. Also the loads that are generated by the hydraulic jacks on the rings, and analyze this in detail. Our next model we have, but we are only going to show a video, is the full tunnel excavation and the effect on the surface and the possible displacement on top. Also the possible affection to other constructions, model, and the full effect of this. So CivilFEM, you have a very good tool to analyze in detail and with nonlinear analysis the fiber reinforced concrete behavior for tunneling and for these ring segments, just ensuring safety, and just after performing, after checking CivilFEM results with the beam test and the lining segment test, checking the real test with CivilFEM results. So you can perform full models with those properties, generating here the rings, and just calculate the global behavior of the excavation process. So well, this is the first example. Second example we are seeing is fiber reinforced concrete pavement. We have solved, I'm going to solve the model. This model is a 10 meters slab. We have created symmetry boundary conditions in both sizes. So we are only modeling 5 meters, and the model is solved for different days. The initial day is day 3, when we have placed the concrete pavement on it, concrete layers, and then we've been solving the model for 7, 14, 28, 60, 90, 120, and 336 days. The target of solving for these days is just calculating the shrinkage effect on this model. For the shrinkage effect of this model, we have calculated a variable shrinkage on the thickness. Shrinkage will be higher on top than on bottom. On the bottom with the soil contact, there is less water evaporation, so it has less shrinkage. So it will generate a gradient on the thickness and possible gap and lifting on this part. And after solving all these days, we have applied a overload, a traffic load on it. Those traffic loads, we can plot it here. So here you can see the traffic load. That is a 65 kilonewtons load on every wheel. So there are 2 wheels, and the target of this model is analyzing possible cracks on this model. For this, in the other lining segment, we've used a high content of fibers. In this model, we have used low content of fiber. So here you can see for this variable softening modulus, it is just there is not a hardening or almost a horizontal branch. It's a reduction, but with almost a residual stress. And well, for seeing the shrinkage effect on this slab, we are going to plot vertical displacement, set vertical displacement. So well, for the first load step, you can see to the slab weight, there's a small settlement, and well, this settlement is not constant. There's less settlement on this corner, and then we start applying sink rates for the following days. This is the result for day 7. You can see there's a small lifting here at the corner. The scale is very big. It's a 3000 scale. For having a best global plot of what is happening in the model, I'm going to keep constant this scale to 35. So all vertical displacement are scaled 35 times. And well, just I'm going to leave it like the maximum displacement we are having. So well, for the first step, keeping the same scale in all the steps. Then day 7, you can see there's almost no displacement. Day 14, these values are in millimeters, and we obtain in less than 0.09 millimeters, so they can be neglected. Now we are having 0.5 millimeters, so it is starting lifting this corner with a small gap. And now from day 60, we start having a gap. And now displacement is around 1 millimeter. And well, after 360 days, we have this lifting. And then we apply here a traffic load. So after that traffic load, we obtain that there's deflection on the bottom direction, and it is creating tension stresses on this part. So well, we are going to analyze possible crackings on this model. We are using a nonlinear material. So well, let's plot strain and maximum principal crack strain. And well, I'm going to do the same, just keep the scale constant. I'm going to see how these cracks are created from the first traffic load. Before a traffic load starting, there's just very small cracks here, just superficial, generated by the stress that is due to this gap. And then while applying these traffic loads, these cracks are starting increasing just in the superficial, so these are not important cracks. And after applying the whole traffic load, here we can see that we start having some bigger cracks, around 0.0001 of this crack strain. So now they are big. So well, the target of this model was analyzing the effect of sink rates on pavements and the traffic loads after that sink rates that can generate cracks. So this model was created with fiber reinforced concrete. It is a low fiber reinforced concrete, so cracks are generating. We could increase the fiber reinforced, and also here we have a model without fiber reinforced, and we are going to compare the results with the fiber reinforced behavior. So, well, you can see cracks are wider, are double crack strains that were what we were obtaining with the fiber reinforced concrete. So we can analyze different fiber reinforced concretes and different effects of the traffic loads and the slab dimensions for avoiding these crack generations. And well, this is just an introduction to a small model for introducing as an example of the possibilities of working with CivilFEM for pavements. This webinar, the target of this webinar was having an introduction to fiber reinforced concrete, and in future webinars we are going to perform a much detailed slab pavement, where we are analyzing just partial joints, or just this joint could keep 1/3 of the section connected to the following slab, to analyze just the transmission of these stresses through that crack and the reduction of that, and the effect on possible crackings on this slab due to the considering sink rates, temperatures, and traffic loads. So here in this model, we can see a video of that lifting we have saw during the sink rates, the 365 days, and then the traffic loads that due to this gap generates cracks here. And the last example we have is the precast modules for architectural, for different parts of the architecture. There are a lot of application for this. We are analyzing this example that was also provided by Master Builders. That is the old branch of BAS, and they create, they have a long list of possibilities for fiber reinforced concrete, generating these fibers. And the target of this webinar is combining those data of Master Builders with CivilFEM tools to check our results, compare with them, and offering a unique tool for designs and new applications of these fiber reinforced concrete modules. So in this case, these modules, the target of these modules is creating different shadows on these windows, on this part. This is from a photo, and they are this has 45 degrees angle, and they are supported by these beams that cover only 2/3 of the model. So with CivilFEM, we were generating the model and also comparing with different tests and the possibilities of crackings appear in this model. Well, just opening model, and you can see here we have 45 degrees. We have created a first cell weight configuration. Then we have added wind loads, and the next step is adding here for this pressure or this wind loads is giving a safety factor. Example, increasing 3 times the wind loads, or also the gravity could be increased 3.5. So these are factors that are applied to the loads, and then we can solve until the model is broken and the software stop converging. So so we can obtain a safety factor if this is the structure, a load safety factor, just obtaining the maximum factor where the model converts, and it means it will have the collapse of this roof. So in this model, is a high resistance concrete, C100. This means it has 100 megapascals compression, and the softening modulus, follows this curve, has low fiber content, but high concrete compression resistance. And combining these two options, but the user can check many different options, many different concretes with fiber reinforced different fiber content to analyze which is the best option for this. And in this model, after applied cell weight and wind pressure, which are in this case the most incorporable loads, so we could add snow, any type of loads, and increase those loads until collapse. That is what we have done, and collapse happens with these overloads. Foreseen, you can see there are some, this part is broken with open cracks. There are generated cracks in other zones, and then this has generated mechanisms that these branches has broken, and some of these pieces just get broken. So software start converging because it starts generating a mechanism. So with this example, we can see this video. And here we can see the video where we applied those overloads with a safety factor, increasing those overloads, and just the crack generation and the collapse of the structure. So this is another application, Precast model for any type of construction and architecture issues. So as a summary, CivilFEM is a very powerful, CivilFEM powered by Marc is a very powerful nonlinear solver, and just with a lot of applications for fiber reinforced concrete. The steps to design this any type of fiber reinforced concrete model is first setting the material properties, stress-strain relationships based on beam test. These beam tests are specified, depends on different codes. The American codes, European codes, they have different beam tests with different dimensions, with a induced crack here, and this obtaining the curves force versus deflection to guarantee ductility. With these properties that we can, there are the codes also specify some formulas to obtain these stress-strain relationships from beam test, but we can increase the accuracy of the model, adding extra points, performing a model with following this test and adding these points. In my case, what I did for the tunnel lining segment is using a bottom envelope of this test to be conservative. So my curve for the stress-strain relationship for my model that I obtained in deflection versus force versus deflection of the beam was like the envelope of the minimum values of the test. And once you have selected the properties you would like to input, you can input those properties in any type of models, model it with solid elements, and perform nonlinear analysis, applying loads, the loads combinations you have for a building, with loads, extra loads, and then increase those loads combinations until the collapse of the structure. So you obtain safety factors for the first crack, and you are obtaining first cracks, and for the collapse of the structure. Also, you can obtain a detailing model with the full lining or the real pressures and compare with the small test. And of course, there's a really big application for pavements, just to consider to avoid cracks due to temperatures and sink rates, and to calculate the behavior of these slabs, and also to consider different thickness and different fiber amounts to avoid the cracks generations on these models. So this is the first introduction we are doing for this webinar series about fiber reinforced concrete. Next webinars we are going to have two ones. One that will be focused on this type of slabs, analyzing the behavior of those induced joints that just those joints just for a part of the thickness, doesn't cover the full one. Also, we will see a tunnel with a project concrete, and with that project concrete that will be fiber reinforced concrete, and then adding a reinforced concrete and reinforced concrete layer for another type of concrete, and possible other applications of this fiber reinforced concrete.
Thank you, Roman. Just a few slides to show you how we can share our knowledge using the masters, the finite element method masters. If you want to learn both fundamentals, theoretical and practical application, using a very recognized software as ANSYS, MSc Patron Astron, and CivilFEM. We will start our next 28th course, and more than 4,000 registered engineers already coursed these masters. If you want to focus your learning in just the practical software, you can join us in the International Online CA Education Center. All the learning has a flexible schedule, and the courses are self-paced. And of course, we can always customize your training. Please contact us for any of your requirements. Cyber as well has its consultancy department, and we develop and perform any type of projects: the technical, structural, mechanical, fluid dynamics. So, thank you very much. You will have a final survey, please, which will pop up once you exit the GoToWebinar application. So contact us and follow our social media. Stay tuned to our next webinars.
Well, also, if you are interested in some more details of the examples we saw, we couldn't go very deep on them. So we didn't have much time for showing these examples. It was an introduction, but if you would like a special demo or some other details and information, please do not hesitate to email us and to contact us for more information. Thank you very much.